cloud. Great. This file is inside of your week 10 folder over here. It's at the top up there. If you download it, you can drag it into your ELGS 11 folder. I figured we would just go back to the beginning one to put it in there. Now, during this, while we walk through it, I wanted to just cover a few brief things, and I went a bit overboard with the supplemental material for links. I'm not going to read out the entire comment to everyone, so you folks can take the time to read through it. But this is essentially a bit more of a focused area of what you'll be familiar with, or what you should be familiar with when we take this final next Tuesday, November 23rd. As a reminder, the final will start at 5:45 p.m. in that classroom on November 23rd, and you'll have 2 hours and 15 minutes, so until around 8:15 to take it. It is around 11 questions. The first few questions are focusing on the, I'm recording, right? Okay, the first few questions are focused on the singly linked list and doubly linked list. There's another question regarding, similar to what we did during the midterm, about how if you are given a function, like do something, what we need to do to be able to trace the output and everything too. So remember, during that one, remember the different ways of how forward recursion and backward recursion works as well. A few of us went over the midterm together. And it's actually based on when you do the work again, right? And so if you do the recursive call first, before you do any of the work, it's going backwards. If you do the work first, before you do the recursive call, it's forward. Also, so these, I feel, again, we'll go through these examples that are pretty similar during this session, but there's also a bit that I wanted to focus on the min and max oriented heaps. And I know when we got to around this part in the quarter, we kind of shifted to more asynchronous, where you would watch the videos. And during this lesson, I won't delve too deeply into concepts and lectures. I'll just more so focus on like some of these ideas that you're being expected to know on the final. And we're also going to be taking a look at these different versions of quick find, quick union, and weighted quick union. And what we're going to be focusing on with these is more so how the different nodes are organized when you're actually drawing them out, and essentially what some of the best and worst case scenarios are as well with those. Now, this big block of code is just notes that you could read through. There's links to videos on these specific sections. I put these links together for folks. So again, if you're like, okay, I kind of don't really get heap sort that much, go ahead and take a look at the video. There's a brief explanation of it as well. I've also included some timestamps specifically for everyone. So please make sure that you read through this. This shows you examples of deleting and inserting mins and so forth. We'll go through this today as well. But again, there's the timestamp there, so please make sure to take some time to read through it. Here are some more links and sections for the different types of quick unions and the quick finds. Oh, I need to add one more in there. And this down here, we'll go through this a bit later as well, but I wanted to take a look at the timing, and essentially we call them the linearithmic, logarithmic, the different types of timings that we get when we're looking at for loops and everything. But again, I want to make sure that everyone has access to more notes and other examples. So there's some practice questions here. There's some YouTube videos by another doctor at a different university that are helpful as well. And again, these are for your, we'll probably add some more in tonight, but these are for your purposes to look at and to see like, okay, what does an actual n linear runtime look like? Great. So this is available for everyone again in the week 10 folder, the Java file called Final Review AY21. And let's go ahead. Let's see that. So again, if you have any questions or anything, feel free to unmute or in the chat. Message me as well. I'm still really bad at Zoom after a year of it, so just be patient with me with it. But anyway, the one thing I want to talk about before we delve into the code is up here at the top. You will notice it kind of looks confusing, but essentially I kind of put together doubly linked list for us. This isn't identical to the one you saw in the homework, but it is just really, you don't need to worry too much about any of this here. This will all be provided on the exam for you as well. Also, the questions here that are about the doubly linked list, you're more so going to be starting with most of it already created. For example, one question might be like, okay, how do I insert a node in a doubly linked list at the end? And again, you have to remember that a doubly linked list has both that next pointer and the previous pointer. So just remember, definitely try to redo that MyDQ homework with the doubly linked list. Once you kind of nail down the doubly linked list, it's actually easier to shift over to the singly linked list. But again, this is what this block of code is talking about. So for a first question that I put, first question that I put together for us is completing a function that goes ahead and traverses through a singly linked list for us, and it's going to sum up each of the negative items in the list for us as well. So with this one here, I kind of wanted to get a feel for how everyone is. We can kind of do it together, just so I'm not talking into the ether of Zoom the entire time. So let's just say that I already have my linked list set up, and I believe I have it here as well. So if you take a look at the output at the top up here, I have a singly linked list, and I have a -5 to a 4 over to an 11 over to a -12 and then to a 12 at the end. So right now I'm getting this expected answer of 17. But I'm actually getting 0 here. So what would I need to go ahead and do to get started here? Can anyone give me an idea of what I might want to do at the very start to start my traversal through the linked list? This is a singly linked list again.
Node X is equal to first.
Excellent. So in our, let's see here, I already have the node X brought in, and then on the final, it'll be a bit easier for us. But again, this is just practice for us to look at. Essentially, what you would like to do on the final when you're writing it is you say, hey, this is going to be the first node that I'm starting off with. For our purposes here and what I put together, we're assuming that the X are brought in is first. That's fine. But essentially, Ryan, you're correct. You want to start off with the X1. So I'm going to go ahead and I'm actually just going to recreate this node as a start node. Let's put it over to my X. And now, there's a few different ways that we can traverse through a list together. But what was the one way that I mentioned during class to make sure that we don't kind of encounter these errors? What did I say we should check if we are traversing through a singly linked list?
To make sure the first is not null.
Excellent. So even before we go ahead and try to start into it, and in our purposes here, I called it, first S, but you kind of get the idea. My first S, or first in my singly linked list, if it is null or anything, our purposes here, in the test, it will tell you maybe return 0 or return a 1, but essentially check for nullity at the start. And you might even want to do that before we even take a look at anything else. And again, on the directions, it will tell you either return -1 or 0. But essentially, if we have a first starting off a null, we want to make sure that we don't go into it. Now, I want to go ahead and show sometimes on the midterm as well, we might have encountered something, and let's just say I'm using my start node. I'll say, okay, I want to go ahead and go forward here. And I want to go ahead and check if the start node.next is not equal to null. Now, as I said earlier, for our purposes here, it's totally fine if you make the proper adjustments to do this as well. You can always check forward into next to see if it's null or not. Where does the danger arise if I start doing stuff like this? What might happen if I go ahead and do like x dot next dot item? Does anyone know what I might encounter? It would be that null exception error, right? So if I go ahead and can I annotate while I'm talking? Great. So if I have, oh geez. Sorry, Zoom is the hardest thing I've ever used. So if I go ahead and I have my node here, let's just say it's X, and I want to say, okay, I want to go to my next, which might actually just be null. If I go ahead and go to next and I try to access the dot item, it might give me that null exception error. So again, just to be on the safer side of things, it's usually good to not try to access the items of .next. It does depend on the way that you're writing it, though. There's multiple ways to write these, as I've said multiple times. So don't think that this is the Bible way of doing it, right? But again, it's most likely the easiest way and safest way if you go ahead and say, hey, check if the current node that I'm on is not equal to null. Now, if I go ahead and in my scenario here, I need to return a type of sum that sums up the negative items. What should I do after I make sure that I'm able to access my node? What do I need to check for? Does anyone have an idea of what I should write in here?
If start node dot item is greater than 0 or less than 0,
Less than 0, great, right? And now what does that tell us, Ryan? That it's a negative
that's
number, right?
negative. Yeah.
Number, great. Put that here. Now, what should I do next if I went ahead and I'm inside of this start node?
Well, I would have a variable before the while loop of double sum is equal to 0.
Great.
And then it would be sum is equal to sum plus start node dot item.
Excellent work, Ryan. So essentially what we're doing here is we're saying, hey, I know for sure that my start node is not null. So if I'm inside of this if statement, I can fully say there's no way that this is null. And so what I'm going to do next is go ahead and add up my item. And I don't need to worry about it being null or getting a null exception error because I know for sure that it's not null. I didn't. Okay, great. Now, after I go ahead and do that, what's the way that I can traverse to my next node in the list? Well, usually the way that we do it is we're going to say, hey, take my start node and set it equal to the next of that start node. So again, it's just going to be moving it down more. And again, maybe I'll make this a bit more easy for us to, I'll just put it as cur for current. But essentially, this is one way that you can iterate through an entire list, a singly linked list. And then I'm just going to go ahead and return the sum after I went through it all. So I believe these tests should work. If they don't, I'll fix them up after the session here. This is a Java file I kind of put together for us. Great. Okay, so I do know what I'm doing. So we did get -17 now, which is where we see I went through each of the items, summed them up, and then went through it. So again, everyone, you could definitely do cur.next. It's not equal to null. You can do it any way that you'd like, but please remember that if you approach it a certain way of accessing .next, you're going to have to account for scenarios where it might not account for, or excuse me, that you might not need to worry about if you just focus at the specific scenario. Now, where is a scenario that I might encounter something going on where it's going past, or excuse me, where I need to keep track of two things? Most likely that remove scenario, right? Where I need to, what do I need to do in a remove function in a singly linked list? Let me pull back up my, right. Again, in a singly linked list, if I'm going through my list right here, and I say I want to get rid of this guy, how do I actually get rid of him? Well, if I say that, okay, I found this guy, now I want to delete him, I actually can't do anything in a singly linked list. And why is that? Because I have no way to move his pointers around. Because what's keeping this node X inside of the list is his pointer in the previous node. So what you would want to do in this scenario is maybe have a Y, previous, current, whatever you want to call it. Always keep track of a node in the back behind the item that you're about to delete. So when you get there, you can cut off the next pointer to the X and then move him over to this one. Again, everyone, this might be redundant for some of us who might be familiar with it, but again, just make sure in a singly linked list that you always stay one back if you're trying to delete something. To really harp on this point, there's a method called remove in mylink2.java that we did eons ago, right? And inside of that method, if you delete it and just try to redo it again, you'll be good to go. And later on, we could try it out together. Now, as a pop quiz for everyone, why do I not need to stay one back inside of a doubly linked list? What do I have inside of a doubly linked list that makes it so I don't need to keep my previous a previous node?
A pointer that points backwards.
Excellent, Michael. Great. A plus. So now we have a pointer that points backwards. So if I hit this X, I can go ahead and track my way back a different way. So again, different data structures, different styles, but again, the deleting and adding shifts a bit based on that. Now there is, let's see here. Let's see in the how do folks feel about the singly linked list and the manipulation and problems with those? Do people feel pretty confident with singly linked list, or are they a bit hazy still for everyone? Just as a general, like you can put a reaction in your Zoom, Heather. Like what? Great. Folks are stunned into silence. Great. Okay. And again, there's that my link too really focuses on singly linked lists. So if you go ahead and delete them, that would be good too. Now, essentially here, I just wanted to, I won't go through the entirety of this second problem, but what would happen here, excuse me, is you want to go ahead and check if there is more positive items than negative. It's a Boolean value. So this function, it goes through a singly linked list. You're going to return true if there's more positive than negative. Otherwise, you'll return false. So again, same idea here. You're probably going to want to keep a counter to see how many negative and positives you has. But it's essentially what a question 2 is asking for you is just to make sure that you're able to get through the entire list there. Now, I want to go ahead and these two are for doubly linked lists. And there's, we're kind of focusing on the manipulation of adding and removing items or nodes from these areas. So if I go ahead and just run this file again, if you look up here, this question tree remove at tree, what this function is asking for us is to go to the position starting at, in this scenario, I'm calling it an index. So at index 3, essentially of this linked list and delete it. So essentially I go from 0, 1, 2, 3, and I see that I have a node of 91. So what my expected answer should be is to go from 41 to 21 to 31 and then to 11 so that the 91 is removed. Now, this is where the drawings and stuff, and we kind of focus this on my DQ as well, where it can get like a bit like you're drawing like a madman about these pointers going everywhere. But essentially, if I have my, let's just take a very, let me get it, I'll go back to blue. If I went ahead and let's just look at, let's see here. Let's just take a look at this section right here. I'll just make a 21, 31, 91, and 11. And I'm saying, hey, this guy right here, he needs to get moved out of it. We remember, as Michael reminded us, that not only can we go forward, but now we can remove the idea, or excuse me, we don't need to keep track of what's behind us because we have this previous pointer. Like so. I apologize in advance for my drawing skills, everyone. But essentially, I have this 91 right here. So can anyone tell me if I have a node is called X, and this X is linked right here to 91, how do I go about and remove X from my doubly linked list? Can anyone give me an idea of what I should do first?
First, you would need to remove the next pointer.
Excellent. So the first thing here is that the way that we need to try to remove this node of X from our list here is we need to make sure that there's kind of nothing pointing to it, right? So what we need to get rid of is this guy here so that 31 isn't pointing to it. And we also need to make sure that we get rid of this guy here so that 11 isn't pointing back to it. Does anyone notice something that we didn't get rid of? You could see that we actually didn't get rid of the 91 pointing back and the 91 pointing forward, because when we traverse through this list starting at first, which is up here at 21, if there's nothing pointing to 91, either previously or forward, then it's not there. Even if we have these old pointers there. Again, if you want to do garbage collection, you could do it that way too. But like to get the theory down, you don't need to really worry about these guys as of yet. So to essentially kind of put this into practice, what we would like to do is somehow grab the previous guy here and then grab the next of X and then set the next of previous over to this guy. And if I'm setting the P dot next to the N, what else do people think I should do next? What should be the last thing I should do here? I should set the oh,
You
Michael,
have to
did you
make,
have-
you have to make 11's previous 31.
excellent. Great work, Michael. So now I have to go ahead and say, hey, I have to set my 11 back to this 31 up there as well. And again, everyone, this is really what we did in a my DQ.driver with this. And again, with the concatenation, concat was a really complicated kind of problem where we have this and that, but kind of focus on this, just the one doubly linked list. For the final, you don't need to worry about dealing with two at once. But again, you can see here that we can actually code our doubly linked list a bit differently because we can rely on accessing the X. So for the final everything, because you don't have code and it's a timed final, you don't need to be very focused on like, oh, am I accounting for if it's the first or if it's the last or anything like that. You more so just need to kind of think about the middle or like the meat of a linked list. So essentially something like the one that I have circled down here. So to actually go ahead and code this, I'm going to go and I'll make this guy current. And he's going to be set to the first of this 21 over here. And essentially what I could say here is very similar to what I did inside of my singly linked list. While my current is not equal to null, I could say, hey, of course, the way that I'm going to iterate through it is current is equal to current dot next. But what I could say is if, let's see here. Oops. Oh, sorry. So we could probably say, once I get to my position here, so once you get to the third position, and then I could say something like int count, I'll set that to 0, or maybe my index, because we're dealing with indexes here. I could say, or, you know, maybe I won't do curl minus not equal to null. I could say while index is less than or equal to my position, I want to get to my position. So essentially here, I can keep going until I get to my current. And then of course, if I want to make sure that this doesn't become an infinite loop, I need to increment my position. So I did a bit there. I hicked up at the start there. So let me just show us one more time. I'm putting in a position that's something like tree. And then I need to somehow move my list or my node that I'm working with to get to that position. We don't have the privilege of having indexes inside of a doubly linked list or a singly linked list, so we need to do it manually. So essentially what's going to happen here is if it's 0 less than or equal to tree, I know for sure that I'm not looking at this first guy. I had a 41 in front too. So this is looking like I'm going crazy. So essentially, this will be my 0, 1, 2, and tree. And I want to get rid of this guy here. So I'm going to keep incrementing my index until I get there. So that's all this while loop is doing. And then essentially we could say after we break out of this while loop, once I've hit the position that I need to be at, and this is kind of a way that you can deal with the issue that we don't have indexes. I can essentially say, hey, I need to go back one to grab my previous. So I could say something like previous is equal to current dot previous, right? And then I also said that in my example, I wanted to go forward one more to link them up. Like so. My X. So I wanted to do something that was like this, where instead of having these guys go into the X, they go around it. So what I have now is this previous is this top node. And then I have my node D of, I'll call this one, I'll just call it next, but I don't want to confuse folks too much. Let me just call this next. Let me call it like that. So currents next and currents previous, like so. And then I could say something where what would the current stat next be? Well, that would actually be equal to current stat next. So in this scenario, again, you would need to do something a bit different, right? If you're going to the end of the list or if you're going to the start of the list. But for our purposes here, let's just go ahead and assume that we're kind of in the middle somewhere, just to make our majority of the loop. And then what we would say is, how do I get these red lines here? Well, the first red line is actually my current previous is dot next. And if I want to go ahead and set this to the other next that's down here, what do I need to set this to? Does anyone know what I should set this to? Again, my X is right here. And if this is my previous up at the top, I can set it to the X's dot next, right? Or the currents dot next. Let me, I don't want to throw too many variable names around. So this is current. Cool. Now, after I go ahead and I set that to the dot next there, I also need to say, oh, hey, before I finish up here, I need to make sure that I have no links to this node. I need to make it removed from my set or my linked list. So then I could say something where it says current next, that previous, which would be this red line, is going to be equal to the currents dot previous, which is this blue one. So again, this dot next right here, this line of code is focusing right here. And then this line of code is this guy right here. So again, this is kind of with the middle of it. Of course, if we're going to the end of it or we're going to the start of it, it'll be a bit different too. But in general, we want to make sure that whenever we have this doubly linked list, not only do we need to worry about going forward, but we also need to remember stuff going backward too. Now, I believe my main method should run with this once I fix it up, but it might not run, and I'll fix it up for us after the session here. Let me see here. Yeah. That's just, I put together a small test, but again, on the paper items there, that's fine for our purposes here. I just wanted to make sure that we see the general idea of how this will run for us. So again, that's kind of the purpose of using a doubly linked list, where you go ahead and not only do you need to worry about what's going forward, you also need to look at what's going backward too. Now, for this idea where we have a position and a val, where we want to insert something, maybe at a certain index, it will be essentially the same type of idea, but a bit reversed. Let's see here. Get that pen. Let's just say that I have a doubly linked list of 2, 3, and 4 here. And I have it at 0, 1, and 2. And I want to say, hey, I want to insert a 1 at the position right here at index 2. What we would need to do is go ahead and somehow make this new guy fall into place right here. And so what we could essentially do is, using that same logic of iteration where we have our indexes less than or equal to the position, we could go from 0 to 1 up until 2. Hey, 2 is the position I want to put this into. So what I'm going to do now is, I know that my current up here is 4, but I can also access the previous like so. So what I can essentially say is that I now have p.next. Let's just call this one previous. P.next will now point to this new node. This new node's previous will point to P. And then likewise, this new node's next will point to 4. And then the 4's previous will point to this new node here. Let's call this new node. Now, I'm doing this a bit quickly again, but essentially it's the same type of concept where you would want to find a position that you need to go to using something along the lines of this, and then go ahead and modify the next and previous's to make it work. And again, everyone, for your final, you're not going to be asked to be like you're essentially given a very big boilerplate, and it's saying, okay, how would you manipulate the next and the previous this here to put something in properly? So again, you don't need to worry about the specifics because you're not able to run your code and check for nullity errors or out of bounds issues. Whereas in the homeworks, you're able to. So during this homework, I really just want to make sure everyone understands how you can manipulate pre-existing doubly linked lists to either remove or insert items into it. And again, drawing it out is extremely helpful. And making sure that you know where to put these arrows and how you can add and remove things is useful for the final as well. So we just went through remove and insert quite a bit. And I know doubly linked lists have a little bit, when you're saying like next and previous a bunch, it sounds a bit like jarbled. Is anyone a bit confused about doubly linked lists? Would anyone like to run through the my DQ again from the homework, briefly looking at any of the examples, or how are we feeling with doubly linked list? Everyone's stunned into silence.
I think a quick spin around would help.
Sure, a spin around. Let's see here. For the my DQ, Nicholas.
Yes.
Sure. So let me go ahead and just pull this up fresh really quick. All right, let me see here. So everyone, let me. Just get interlude music to play for all of us. All right, so let me pull up. Great, so let me. All right, everybody, just give me 1 second here. I can pull this up for us. It's giving me one. It's in the wrong file. Oh, okay, it's just a concat one. All right, let's see here. Cool. So let me share this here. Great. So my DQ had a few ideas going on with it as well that we could go through. A main one here that I want to really focus on as well, which is reminding us of how we can look at a few of these areas, is for instance, the push right and the pop right, or push left and push right as well. I believe these ones are working for us. Let me go ahead and get my annotating tool out. So again, if I'm dealing with these kind of linked lists here of a doubly linked list, you see here, we do 11 and then 12 and 13. Essentially, once we go ahead and push left, because the important thing about a doubly linked list is that we can toss it on to the left or right, either side, is the starting item here. We're setting it to first, as we've already seen it there. And then this node X, this new node, is one that's coming in. Let's just say it's 10. And what we're doing here inside of this if statement, let's see here, going ahead and just trying to, the first one is checking if there's nullity or if it's an empty list. But what I want to focus on is in this else statement, we notice that old first is set to the original first of this linked list. So this one is old first. And what we also need to remember is that the previous here is pointing to null right now. And the reason it's pointing to null is because it's the first item in the list. The previous always points there. So what we need to do is go ahead and toss this first one, or this 10 onto here, so that it becomes the new first. And the way that we can actually see that in code, I noticed I deleted a bit of my old item there, so I'll just add it back in now. If I want to make this 10 right here, this line of code completes this section right here where I have item pointing back. But what I also need to do is remember that this 10 is now technically my first item now. So what I could say essentially is that first is now equal to X, because this is the first item there. And what else do I need to do? Well, I'm in a doubly linked list and I don't really have anything pointing forward. This is pointing out to null right now. So what I would like to do is go ahead and make this guy point to the old first there. And I could probably do that by, before setting this one to the first, I could say x dot next is equal to old first. And then that would essentially add in that line there. Now, again, the useful thing about these doubly linked lists is that the inverse is essentially can be said for the other side there, where I have the 14, putting it in here. This is my last item. Remember, every doubly linked list has a last and a first, and that's how we could put it in on either side. Pretty similar logic where I try to get to this last one. Essentially, what I would like to do is I know that I'm at the end of my doubly linked list if this is pointing to null. So what I can do now is go ahead and make this last point to this guy called X essentially. So last is now going to last dot next is pointing to X. And once I do that, it's going to make a line like this. And what else do I need to remember? Well, if this is my X is trying to be my new last, I can then say something where it says last is equal to X. And then that essentially removes this one from doing that. But what is the danger of doing this before completing everything? Well, not only do I have a next pointer pointing to this new X, I also need to make sure this X points back to it, right? That's how we traverse both way. So what I could say here is my last dot next is equal to this X, and then my X dot previous is going to be equal to this last. And then what I can say after I do all of that stuff, I could say, hey, last is going to be equal to this X. I'm going to update my last. So essentially you could see here that what I did in this scenario is the inverse or the reverse, or yeah, the reverse of what I did at the start there. And that's just because we're just essentially swapping what we need to do, because one's at the start and one's at the end there. And again, folks, for the final and everything too, the focusing on the start and the end, like once you can kind of get your head around the idea is pretty good. And outside of that, being able to manipulate this middle part by essentially saying, hey, I want to kind of just, you can kind of think of it where it's like you have this list, you grab the 2 pointers, you pull them apart, and then you stick them back together with a new guy in there. So again, it's more straightforward. The only thing is that instead of having to only worry about the dot next, you also have to worry about the dot previous. Again, everyone, for your final, you don't need to be as in depth as coding as you did in the homework assignments. It's more so asking like, hey, what would you need to do to insert this in between these two things here? So once you understand the and what I would say is try out quite a few times inserting into a singly linked list, and then going ahead and making sure that, let's see here, making sure that you get that down, and then you can introduce the previous one. Now, as one more little hint here, some of us might be astute on this. You'll notice that, hey, the way that I can figure out I'm at the last item in my list is if the next is null. How come I didn't have to say anything where it's like in here, x dot next is equal to null? Well, we default our code to do that anyway. We also have it up here where x dot next is null already. So because that's already done, that's totally fine too. It's also a bit redundant. You don't really need to say last dot next is equal to null as the X already has it for us. So again, with my DQ, you don't really need to worry too much about the concat operation because that one's very intense with adding in 2 doubly linked lists at once. More so just really get down to this process of having these 2 pointers go back and forth. And what I would say is you have access to the submissions. So if you submitted my DQ, you can have that save file and then go ahead and delete all of the, this would be a fun weekend party thing to do. You could go ahead and delete all your push rights. So you can delete push right, pop left, and pop right. You don't really need to worry about concat deletes. I would also delete as well to try to redo, and then just see if you can kind of grasp it. And then the main thing is though, is that what I would say is while you're redoing it, if you are doing these and the errors that you're getting is, hey, first is a little messed up or last is a little messed up, but you were able to pass the tests that are in the middle, you're on good shape for the finals. So just make sure you focus on it, but please do remember to know how the first and last work. But focusing on the meat of it, the middle will be useful for us. That was, sorry, Nicholas, that was a bit of a tangent. Did that help a bit with more the pointers and the manipulation?
Yeah, it helped pretty good. Thank you.
Sure. Yeah, no worries. Absolutely. Again, everyone, anything too fast or anything like that, let me know. We have the office hours as well, or other times too. Now, this is one that some folks on the midterm, I felt a bit bad. You essentially did it correctly, but you did it backwards because of how some of us might have learned how to pop off the stack. But essentially what we could do here is, let me go ahead and run this again. Question 5, as like a spoiler alert, what this prints out for us when we do 4, do something of 4, is it prints out 4, 2, 1, 2, 1. And you might be wondering, okay, why is it actually doing that? And you'll notice here that not only are we doing a subtraction, but we're also doing this division idea as well. Now in Java and other languages too, you can actually divide until you get to a 0. And that might seem a bit counterintuitive to what we're used to, but integer division always rounds towards 0. So essentially 7 divided by 4 evaluates to 1. If you open up your calculator and actually do 7 divided by 4, it's 1.75. So you might be thinking 1.75, I'm rounding that up to 2, because that's how we usually do it. In Java and programming languages, we round down, so it'll be 1. So essentially you keep dividing, you'll hit your 0. And that's why, if you could see here, we don't actually get an infinite loop, because our n is greater than or equal to 1. At some point, our n is less than 1, which is most likely 0. So let's actually walk through this kind of quickly here. If I go ahead and I call do something with 4, so let me do my, is there a better color than, I guess blue is the best one. If anyone's having a hard time seeing or anything, please let me know. But I'll just stick with blue for right now. So if I say do something of 4, I enter into my if statement here. If n is greater than or equal to 1, standard out print n. Okay, so what does that mean? Okay, just go ahead and let me put up a few areas here. This will be my console. Well, it already is, so I'm just going to put my 4 down here. Let's call this one the console. And this up here will be my call stack. So I already print out my 4. Now I say do something n minus 2. So now I go ahead, and after I called 4, I now call something of do something 4 minus 2, which is ds of 2. So now I have this ds of 2 up there after I subtracted them. And now what do I need to do next? Okay, well, I kind of want to go down here, right? I might need to go to the next line, but no, I actually have this priority. Whenever you have a function, a recursive function like that, before, if it's not saying return, if it's just saying something like this, it's saying, hey, you need to do this function right now with the parameter I'm giving you. So now I jump back out of whatever I was doing in here. I might still have some more things to do inside of here, right? And I have my standard out print of n. So even though I might have needed to go down a line, my ds of 4 is right here right now. I need to jump down and print out my n, which is 2. Now I go ahead, and then after I do that print line, I do something n minus 2. Now this essentially does n minus 2 minus 2, which is 0. And what that will do next for me is I won't be able to jump into this loop or this if statement here, right? Because 0 is not greater than or equal to 1. So am I done here? Is 4, 2 my last statement here? Why am I getting 1, 2, 1 over here? How come I'm not done? Any takers? So again, oh, yeah,
Because of the other recursive function, the other do something.
excellent, Ryan. Great work. So what I said earlier as a little hint, I'm like, hey, what about this stuff right here? These calls and stuff don't go away, right? You still need to do them. They're on the call stack. So you can imagine like, like a big stack of pancakes, and in the graph does I remember how it kept stacking up for us? Essentially, we still have a bit of code to do. And where did it do that for us? Oh no. Okay, good. Where did it do that for us was around here where we had DS of 4 and 2. So what I go back to now is I go ahead and I say, let's see here, draw. I go back to my n-2 here. And then I do something after that one. My n was, let's see here, my n was 2. So I do, let's see here. What? Oh, 1 over 2. So that should get me my 1 there. And then essentially, I want everyone to remember that we're going to enter back into these loops here and kind of keep continuing with our recursive calls. So again, everyone, once you hit the 0, the main point of this is even though we might have hit 0, we still need to do these rest of the recursive calls that are there. So we enter back into this do something of n divided by 2. Our n at that point, let's see here. N is 4 and then 2. We have our 2 divided by 2 in this part here after we jump back in. So 2 divided by 2 will be our 1. And then we go ahead and let's see here, go back up to our n. Then we just continue with our division. So I'll go ahead and also let me add in a graphics of this before I release it to everyone too, so we can see the outputs. I haven't made a graphics trace for us, but I think that would help as well. Let me show another one as well in the playground midterm here. See here. This was something that we went through together in class for us. But again, there's another scenario here where we were doing the forward recursion, where essentially after we do something, we're doing a bit more in this one. But you'll notice here that we're getting the inverse of what we had. The midterm itself had the answer of 421. Oh, this is the wrong one. So everyone, I'll go ahead and let me, I'll do this for us. Just in case folks want some more practice with these do something problems. It's just neat to be able to trace through them and then write down on your call stack where you jump in. But again, the main point I want to say is that if you are here at this one and you jump back up to your recursive call and then you return to it, make sure that you don't forget about the guys underneath it. There's still recursive calls that you need to make that you will need to return to. Again, everyone, the do something I don't think will be too convoluted for us. It's something that we'll be used to. I'll put in the midterm version of it as well. But the recursive calls and call stacks, just remember if you hit your if you hit this if statement where you need to break away from it, remember that you still have that stack that you might need to look at as well until you actually get to the end and you have no more stacks. Great. Let's see here. Great. So there's a bit essentially, your first half of your final is essentially going to be, hey, insert into this linked list, modify this linked list and so forth through doing some operations on the linked list. Christina has a few SI sessions as well that are useful to attend as she's doing some more examples with them. We didn't cover these in depth during lecture time, and I wanted to cover a bit of the heaps and how they're operating with us as well. So let me go ahead and in the notes up here as well. Let me see. Yes. So right up here, there's a big chunk of notes that are talking about heaps and heap sorts and operations on heap sorts. The two main things that I want folks to review is being able to delete the min or max from an ordered heap, like that tree node structure. And then also being able to translate a heap that you see into an array. So I'll go ahead and I'll do an example of this. Let me get my notes together here. So everyone, I have a bunch. Let's do and excuse me. So what the first thing I would like to do here is go ahead and try to build out a heap. And you'll see here into question 6 that I created this, or excuse me, I'm asking you to, given this index value here and the values down here, create a minimum sorted heap. So a min sorted heap is one where the minimum elements are on top and we go down. And what I would like everyone to do, let's see here, is go ahead and I could do it on the screen for us, so you don't need to, but definitely practice this on paper because you're going to be asked for it on the final. So again, I'm given this array here of 6 elements. Let me see here. And everyone will notice that the first element, this is just given to you in the exam as well, but it's empty, right? And does anyone remember why that first element might be empty? So again, when we're dealing with heaps and so forth, oops, that's the wrong one. 1, 2, 3, 6, 4, 5. We have a little bit of an algorithm that we use to determine the parents and the children of a heap. And what was that algorithm again? Well, to get to a nodes, if I'm at index 1, how do I get to my left child's node at index 1? Well, I times my index position. In this scenario, we'll call it k by 2. Now, what happens? Let me call this left. How do I get to my right-hand node? Well, the right-hand node should just be 1 over my array. So I times my index position by 2, and then I add a 1 to it. So the reason I bring this up is that we can also use another item to get the parent, which would be k over 2. And we want to make sure that this k can't be 0, right? Because what happens if you divide by 0? You like kind of blow up the computer, right? So you want to make sure that the first index that you're dealing with, the 0th index, has nothing in it. You don't need to worry too much about that. I just wanted to bring it up as some of us might be like, why is there a dash inside of here? So essentially we are ignoring the first array index and we're focusing on the other part. So using this type of logic here, I want to say, hey, can you go ahead and build out my minimum ordered heap? And the first thing I'm going to do is, okay, well, I know I have my first index right here at 1, and it's the value of 1. So I'm just going to go ahead and put 1 up here. Now, every node has the ability to have 2 children a part of it. So I'm going to go ahead and put out my 2 arrows here for my 2 children. And I'm saying, okay, how do I get to my left child? Well, it's 2 by 2 times k, which is my index value. What is my index 1? So, okay, 1 times 2, which is 2. So now my minimum ordered heap now has size 2, and it has the first item and then the second one over here. Now I'm thinking, okay, how do I get to my child, a node over here? Well, I do 2 times 1 again, 2 times k, which is 1. So that's 2 plus 1, which will get me 3. So now I have this ordered heap of minimum ordered heap of 1, 2, and 3. And now I'm thinking, okay, well, how do I get to the children of 2? How do I make these children? Well, 2 is at which index? Well, fortunately, it's at index 2 for us. And then what's 2 times 2? Well, to get the left side, it's the 6 over here. So I'm actually going to put my 6 right here. And now I'm saying, okay, well, how do I get this right element? Well, 2 times 2, which is 4, plus 1 is 5. So this will actually give me my 4th one. Now, everyone, a main point that I want to show is thinking, hey, logically looking, doesn't the 6 come after the 4? How is this minimum ordered? The order that your array is in and your heap isn't actually completely ordered. It's ordered to this idea of minimum at the top. And what we're doing here in this scenario as to why we're doing this, what we want to do is if we delete the very top node of any heap it should put it into an array that's ordered for us. So essentially, if you ever look at that heap sort kind of like algorithm that's going crazy, do folks remember when we watched that in class? It kind of did a bunch of different heaps at the start, right? It was like going a bit nuts with a few of them. And then all of a sudden, there was an array at the back that came down and was fully sorted. That's what happens when you delete from the heap. So what we're doing now is we're trying to organize our heap in such a way that when we delete from it, we'll get an ordered item, a minimum ordered item. What do you do with a maximum? It's just a minimum reverse, right? The items that are bigger go on the top. So I don't want anyone to be confused as to why the 6 is coming 4 to 4 here. I also don't want you to approach it with this idea where it's, okay, this is index 0, 1, 2, 3, and 4. You need to rely on these operations here in order to determine your child and your 2 children nodes and your parents. So that was just a little bit of a tangent there for us, but I just want to make sure everyone sees how this node is built out. And now you'll notice I still have my element over here, my last one. And I just finished up my index 2. So I'm going to go over to my index or my number 2. So I'm going to go to tree. And you'll see here that at index 3, I have a 3. And then what's 3 times 2 is 6. So now I have a 5. So my left side here is 5. Now you'll see here, just like in the examples you might have seen in the videos or in class, a complete balanced binary tree is one where the right side is missing a bit. And again, the idea here is that the array is always going to be a completely balanced tree for us. So everyone, this was a very briefer example, but essentially being able to, please remember for your final, these commands here, or algorithms, I guess you could say, of how to try to find the left and the right node, and K will be your index there. So K will be synonymous to index. And again, given an array, something that looks like this, can you make a minimum ordered binary tree? So we went through a bit there. Does anyone need me to redo this or do it with a different array, or how are folks feeling?
So with a question about this on the final, how would you do it without making code? Because on the final, we don't have to make code. We just have to like generalize it.
Yeah, so that's a good question, Zach. So what I would say is essentially on the final, you will be given like this piece of information here, an array with a few numbers at the top, and then you would just use this section right here to do it. So essentially you would say, hey, what's at index 1, my first element will be at the very top up here. How do I get to my left and right children of my first element? 1 times 2 is 2. That gives me to my second index. So that's going to be 2. 2 goes down here. 1 times 2 is 2 plus 1 is 3. And that brings it down here. So again, you would just reference those abilities. You would reference the left child is getting the 2K, and then the right child is getting the 2K plus 1. Let me see here. In this section right here as well, we go through it in the videos and we don't really use code. You can see the code in the left side of the video of what we're doing, but essentially we're drawing it out in the videos as well. There's not, you can make this minimum ordered heap without having to use code for it. Okay, let me see here. Nope. Okay. So folks, let's go ahead and I want to focus a bit more on, so again, that's another thing is you won't really need to be asked, you won't need to be worried about like, okay, given a heap, translate it back, more so just understand how the heap and the arrays are working with each other. The other thing that I want to talk about here is deleting. So the one thing that I showed us earlier, and I mentioned earlier, was that heap sort essentially sorts a little bit of our information into a heap that has a certain kind of order so that when we delete from it, it sorts it into an array coming down. So essentially what I want to do here is try to delete from this top one up here. And I want to just use a different tree so that we don't get bored looking at the same one. See here. And I'll go ahead and let me do 2 and 3. I apologize again for my drawing. I should probably get a stylus or something. Huh, sorry, that looks rough. So MS Paint lesson. Cool. And then let me use 10, 7. Let's do 9 and 8. And using this idea here, what I want to do is, let's say that I want to delete the min. So can anyone tell me, based on just kind of heap, it looks a bit messy, but where's the minimum value right now in my heap? What value is it?
The 1.
The 1, excellent guys, right? So it's up here. And what is this? Oh, that's the root of my heap. That's the first item pretty much. So what you want to do whenever you delete something from a heap is you want to swap your first item with your last item right here. So you're essentially going to swap them. And I can just draw this out here. Here. So this would be 1. And now this would be 8. And in the code, in the videos that I've linked here as well, you'll see in the code what it says is essentially A, if I have an array of n, and n is the very end of my array, if I set that equal to 0, it's just essentially going to remove this guy from my list. So that's what the code is kind of looking like. For our purposes, we're not, we're drawing it out conceptually. So essentially you have a piece of code that deletes it for us. And now we have a removed item here. Now, can anyone tell me what might be an issue here in my minimum ordered heap after I do this delete min operation? My 1 is in a sorted array somewhere, so that's fine. But what's going on with my heap now? Folks see that my 8 up here is at the top of my minimum ordered heap, but that's not the case, right? It needs to be near the bottom. So essentially what you need to do now in the heap videos as well, there's 2 algorithms called sync and swim. Swim is where we go up. Sync is where we want to go down. We're going to sync this 8 into the bottom of our heap. So essentially the way that we can sync this is there's a process that we can go through, and we're going to need to look at the children. So essentially we need to look at the left child and we need to look at the right child. And these 2 children are going to have a little algorithm that we can focus on. There's 2 scenarios. If there's no right child, if there's nothing here, let's just say, for example, there's nothing here. That's not a balanced binary tree. The champion is the left side. But let me do this real quick. So if you don't have a right child, the champion is going to be the left side. Or if the left-hand side child is smaller than the right-hand side, the left-hand side is the champion. So essentially you will pick the left champion if there's no right. Sorry, everyone. Or the left is less than the right. And otherwise, if these 2 scenarios don't occur, if there is a right and the right is bigger than the left, then you'll take the right. So that will be the champion there. I'll write something in there later. So in this scenario here, can anyone tell me where 8 should go? Should 8 go to the left child or to the right child? If I'm swimming 8 down my minimum sorted heap, where should my 8 go?
To the 2 will replace the 8, and then 8 will
Excellent.
replace 4, and then down to, yeah.
Excellent. All right, let me keep up with you, Ryan. Great. So again, Ryan's excellent, right? So the 2 is less than the 3, so the 2 is a champion. Now I say, okay, well, my 8's here. Is 6, is there a right child? Yes, there is a right child. Is the is the left less than the right? Well, it's not actually. We have the 6 is greater than the 4. So what happens now is that the 8 will swim down into here. Let's see, 8. And now I have this scenario. Okay, where is my 8 going to go next? Well, I actually don't have a right child, and I don't really have a comparison here either. And because I want to make sure this guy's my parent, he'll just stay up there as well. Like, you can't really do something like this, you know? Where's the parent in this scenario? So you want to make sure that this is maintained as a complete balanced binary tree. And every balanced binary tree takes the form of this type of thing at the bottom, where it has one child of the left, but no right. So in the final, when you're asked, hey, can you delete the min? What will this heap look like after you delete the min? That is the process you're going to take, okay? Now, the same occurs for min or max as well. And please make sure you take a look at the heap videos on that. And what I want to also say here is, okay, I have this new, let me go ahead and reset my tree to a different one here. See, this is 1, 4 tree, 6. Cool. So let's keep this as it is right here. But essentially what we're going to do here in the delete, we swapped them and removed it and swam it down. Let's just say that I want to insert 2 into this scenario here. What you're going to do in this scenario is you're going to want to swim 2 up based on its parent, which is this one is a bit more straightforward. So essentially, I would go ahead and I would have my 2 compared to the 8. Because I'm in a minimum sorted heap, I need to make sure that this guy becomes the parent, because we need to maintain an order, right, of our heap. A parent can't be bigger than its child in a minimum ordered heap. So this guy would become 8. This would become 2. Now, are these guys less than each other? Yep. 4 is less than my 2. So then I can go ahead and swim this guy up here. So now I inserted 2 into this little heap that I created, and I just swam him up into his position. So the situation where we insert's a bit more straightforward, I would say. It's a bit easier than the delete from. But again, to remind us in general, when you delete something from a heap, you swap the top and the bottom, and then you swim that previous bottom to the new bottom. And then when you insert something, you put it at the very end. And again, what did I say earlier? Every complete binary tree might have either no child or it will go into here next. You're going to want to put it in at the bottom and then swim it up to the top. And those swim and sink are functions that you see in the algorithms textbook, and you also see them in the videos. So that's not just like a random word for them. That's what we determined they are. Okay, so I just went through quite a bit of heap logic of working with these nodes and these roots. Again, that big chunk of text right there from line 31 and down is all about this. So please make sure I even put the timestamps in here for more help. So does anyone want me to go through another example of swim or insert, or how is everyone feeling? Again, I think the main idea that I want everyone to know is that even though like this isn't a sorted array, right? This is an ordered heap. That's the difference there. When we delete from this ordered heap, we're going to put it into a sorted array. And as a little pop quiz, does anyone know the running time of this heap sort? If you read the sections. So again, the runtime here, because we're kind of dealing with half of the ordered items, we have this log n because we're having these operations, but we still have that array at the back, so we still have that linear time. So the runtime of heap sort is actually n log n because you're dealing with 2 of them, but heap sort is a nice way of introducing these idea of order. Now, really to reiterate a point here, I just want to go ahead and show us what this would look like in array form. So I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 spots here. Let me see here. Do I? Yep. So I have 10 nodes. But what did I say earlier? That the first item in each array is going to be that little empty spot because it's a heap. So let me go ahead and just do this for us really quick. And 11. So thank you everyone for being okay with my artistic skill. There's a reason I'm a CS major. See here. Okay. That looks rough, but we'll get the idea. Cool. So Essentially here, my first one is going to be empty. And okay, where do I even start with trying to transverse this to an array? Like where do I even start to? Well, I have my first guy right here, and I know for sure that he's my 1. Now I use what was my 2 algorithms again? My left child is 2 times k. My right child is 2k plus 1. And after I have these two, I can essentially convert any heap sort into an array. So what I can say now is, okay, what's my left child? What's 1 times 2? That's the second one over here. This is where this left one is. So I'll put 2. What's my third index at? Well, 1 times 2 is 2, plus 1 is 3. And this is where my right child is. So my right child of 1 will go here. So that's 3. Now, this might be a bit redundant because it says 1, 2, 3 and 1, 2, 3. But essentially here, I can go ahead and go to my next index. So I'm going to iterate 1 down, excuse me. And now I'm at my second part. What's 2 times 2? 2 again is a stagnant number. The k is my index. Let me write that down for us. If you're rewatching it, to just remember that k is index. What's 2 times 2? Well, it's 4. And what's the left child of 2? Well, it's 6. So my 6 goes into 4. Now, what about my right child? 2 times k. Let's see here. 2 times 2 is 4 plus 1 is 5. And so my 4 will go into my 5th slot right here. Let's keep going down. We just finished up with 2. Let's jump over to 3. What's 3 times 2 is 6. So my 5, which is on my left side, is over here. My 11 and my node is the right child of 3. So it's going to probably be 3 times 3, or 2 times 3 is 6, plus 1 is 7. So this 11 was going to go into 7. Let's jump over to 6 now, because I just finished up 1, 2, and 3. What's 4 times 2 is 8. And what's the left child is 10. So I'm going to put that into the 8th index. What is 2 times 7? Or let me see here. Sorry, 2 times 4 is 8 plus 1, which is 9. So I go ahead and put this 7 into the 9th index. Sorry, I confused myself there by looking at the indexes. Here we go. But again, I just wanted to really show off the process of doing this for everyone. Again, it's not, you don't need code for this. You don't need to run anything. It's literally just applying, looking at your tree, just be like, okay, the left child is the pair, the 6 has a parent of 2. And we should be able to do the same thing going reverse. So let's see for 9. How do I get to 9? Well, I just finished up my 7, putting him into spot 9. So now I just finished up 6. So I'm going to go 1 over to 4. My 4 is right here. 4 times 2 is 10. My 9 is on the left side. So my 9 goes there. And then 4 times 2 is 10 plus 1 is 11. So that hits my 8, and that will be my 8. Again, everyone, this process, like first time seeing it or like looking at it a few times is a bit like kind of weird. It's kind of like, okay, there's a lot going on, but just remember in a heap sort, if you're looking at a complete binary tree of a heap sort, this is the process of converting it into an array. And also, if you know how to do it this way, you'll know how to convert it into a binary tree. So again, you can essentially just say, okay, 1 times 2 is 2. That's the parent, that's the child of 1. 1 times 2 plus 1 is 3. So that's the right child of 1. And then you can just keep doing that each time. And you'll notice that this is kind of the way that it will be built out, right? Something like this. So again, that's essentially the heap sorting and these operations on heaps that for the exam that you'll be asked to deal with. And another thing here for the exam is I won't delve too because the drawings are getting a bit excessive. I'm sure I don't want to have everyone go crazy with the drawings. But another section here is after these heap and these operations, after you kind of nail that down, we're going to be taking a look at the union find and the quick find items. And you don't need to memorize essentially what every single difference is. It is useful. So essentially what you would like to memorize for these guys is the different ways that they build out their trees in the worst and best case scenarios. So I'll need to, let me actually grab that up first now really quick so I don't forget this video. So if you just give me one more second here, great. Okay. So these three different videos go through in depth these different versions. What I want to kind of focus on today for our little review is essentially the different ways that these guys are built out. So quick find. Then as a reminder, quick find, the most important thing about that is that its find operation, when we're looking at the testing during class at the bottom, is that its find operation is like almost instant. It's a constant operation. And the reason is because we focus on the find concept of it, or the find operation only. But the issue was trying to, let's see here. So Daisy, the drawback was the union operation. So unions could take a bit of time in the quick find. But again, if I have, so essentially for your exam, what you would kind of be asked is listed out a few of these nodes. What is, what's the, excuse me, what might be the best case scenario unioning all these nodes together? So as a general idea here, let me just go ahead and make a few nodes that we can look at. And again, these scenarios are a bit different each time. There is that weighted, another thing that I'll like everyone to use before I jump into this. It's in ALGS 15, test union find right here. There's a bunch of information that we can look at. But if you comment a few of these out, oops, I'll leave that one there. In the main method, where's my main? Let me do quick find right here. I just shouldn't break my computer. Cool. So for this part here to help study as well, please go into the test union find and spend a bit of time just kind of uncommenting these guys and saying like, okay, well, what's the difference here? And you'll notice here, what was I saying earlier? The connected is very constant. It's very good. The find operation, but the union gets pretty bad. And if I kept this running, it would eventually make my PC a bit slower. So what we want to do here is the test is going to ask you, okay, why are these a bit rough? What's going on with the unioning and everything? And in these kind of worst case scenarios that we'll be dealing with, let's take a look at the scenario that looks like this one here. 2-0. Let's say that I perform a union operation like this, where everything is union with 0. What happens is that the in this quick find, the union operation isn't the best. So we go ahead and we kind of arbitrarily pick the winner. During the video and during class, we pick the right side to be the winner. So what you would actually get is if I do 1 and 0, what you would get is having a 0 like this. This is going to get a bit messy. Do it like this. You would have the 0 above your 1 with an arrow to it. And then if you do a 2 connected to 0, 2 is actually going to point to that guy as well. So now we have this situation where we have this one pointing to it as well. And then we have this tree that points to this one too, in this scenario too. And then we have this 4 and 0 is union, and then 5 and 0 is union as well. So again, if this champion is selected arbitrarily at the right side one, this is kind of a scenario where either in the best or the worst, this is what it might look like. So what I want everyone to study for these sections of the different types of unions and finds is the final is going to ask you, okay, well, what's it look like in the best case scenario if you use quick find or something like that. So you need to remember why these operations are a bit different and then just recall them while we're going through them. So in this scenario, what you might have for quick find, excuse me, is something kind of like a bunch of people looking up to the 0 essentially, like everyone is kind of unioned to them. So that's just one example of what it might ask. Another scenario is where it's the different type of union, such as quick union. Let's see here. And essentially, if I use a quick union, which of course, per the name, the union is fast. If I have this similar scenario, I might have this issue is like, okay, what if I union everything to 0 again, where I have it like this? What quick union does for us now is it actually goes ahead and introduces this concept of depth a bit. So the first scenario, it's a bit random again. It might be 1 or 0. We don't really know how to determine a winner. We haven't built that in yet, but we do know that it could be either one. So for this scenario, I'm just going to make 0 the winner for us. So now I have 0. Let's see here. Let me make sure. Go. Or, you know what? Actually, let me do it this way for us. Just so I'll make it a bit different from 0 being the winner for us all the time. Let's take this scenario where we have like these different winners on the right side for us in each scenario here. What would happen is if I say 0 is a loser to 1, because arbitrarily I'm picking 1 to be the winner, 0 is going to be pointing to 1 because 1 is the champion. And now I say, okay, 0 is not a loser at 2. But in quick union, the issue is that not only does it not just make it its own champion, so 2 isn't going to point to 1 like that. What it's going to do is it's going to point actually to, or it's actually going to take ownership of 0's champion as well. So we saw this in GraphViz, but essentially what would happen is 1 then points to 2. And this continues quite a bit in this scenario where we have this kind of elongated drawing going on. So it's going to keep building up for us. And now, just as a little pop quiz for all of us as well, again, let me remove this. If I go back into my test union find and I go ahead and make this guy run, at the bottom, we'll notice something a bit different. So in quick union, or excuse me, in quick find, we had an instant connected. Can anyone tell me why this connected is suddenly a lot longer than the union? What do folks think might be going on based on what we just drew up here? And you can see here, this is kind of getting pretty bad, right? Like it's already taking 16 seconds. Essentially, the way that this one is coded for quick union is that if I want to check if something is connected, I have to go ahead and start at this guy and then check, okay, is he connected here? Well, he's not. So I got to jump up to this guy. And then you have to search from the bottom up, essentially. And what does that mean? That means that it's going to be linear. So that means that based on the size that we have here, it's going to increase dramatically. So that might be a worst case scenario for us where we have this increased amount of time and we need to figure it out there. So what I would like everyone to do just to practice as well for the midterm is please review those 3 different videos. Again, the GraphViz in class kind of blew up on me during it, so it wasn't that effective. But these videos here, each of them denoted here, you don't need to watch the entire thing. What I would watch is the sections where it has GraphViz showing, and then just read through it and make sure that you understand these different ways that these graphs are laid out and everything too. Excuse me. Great. So that's essentially a bit about unifying. You don't need to, again, it's not going to be like asking you to union together these nodes and draw the heap sort of it. It's just going to be asking you to consider these scenarios for it. So let me go ahead and clear my screen. And essentially another good item to review besides the MyDQ is the MyDQ using stacks. So I did allow a bit more time on that, and there is information on it as well. But the main thing that I wanted MyDQ using stacks to work with is this concept of running time. So we could see that in MyDQ using stacks, the solution that we found was that if we half the amount of items that we need to look through, we half the overall running time. So it made it from quadratic n squared running time to a linear running time. Now, there's a ton of information that I put together here for the running times of items. Let me go ahead and run this one more time here. Good. I added in a little bit of notes here too. Before you reread these ones, there's a little practice problem for each of these. Draw worst and best case, given all these guys too. After you go ahead and read through these, there's a bit of information on running times. And essentially what you're going to be kind of prompted with the exam is you're going to be given a few loops and like kind of ways that they're built out. And it's going to be asked, what do you think the running time of this is? And you have a few options to select from. So again, the main ones that we were looking with, the ones that are pretty straightforward, is that it's linear, right? And why is this one linear? Well, given an array of length n, I'll just call this n. If n is 1,000 and I iterate through it the entire time, the amount of time it takes me to iterate through this is directly proportional to n itself. So if I increase n, I'm going to increase the amount of items I get. So just to kind of showcase some of these concepts for us, let me go ahead and paste this down here. And again, I'm picking the easy ones here. So if my n is 16, let me do my count up here. Plus plus. So if my n is 16 right now, and I have this presumably linear length for loop, how long do you think it would run for? Or how many times does it run? It runs for 16. What do folks think it might run for if I change this to 64? Can anyone tell me in chat or either in unmute what you might think it might run for? Let me put these in here.
64 times.
Excellent work. Great, Michael. So again, it's proportional to n. That's the biggest idea. So if you have a for loop that's running an n time, it's going to be proportional to it. Now, what about these scenarios where I have this n squared here? What's going on here? Well, just to kind of visualize what we're actually looking at, what's happening is I probably should have pre-made these for us, but it's fine. Let me do n minus 1, and then this guy is going to run for count up here. So everyone, thank you for the patience. Let's make n equal to 2 right now. This will be my second one. If I run this one, we could see, oops, it's my count. Let's make this one 16. My examples always break when I'm showing them off. Okay, so it's a little different, not precisely essentially, but we could see here that the more that we increase our 16, the more squared it's going to get. And as a basic, to kind of not make it as confusing, n I plus plus, let's do it this way instead. We could see here I had 119, it's 120, but essentially you're going to, for every iteration of I linearly, it's from 0 to n for I, which we already saw in the previous one was linear. I'm going to do another linear amount of work, and that's going to boost me up to my n squared. And you'll notice here, try this one here as well. 6. There's a few different scenarios that we could look at where it's also less than n or it's also less than I. And I want to make sure that folks take some time with these notes up here to kind of fiddle around and play around with the different timings. So I have a few big notes right up here called supplemental timing notes. There's 2 sections down here that are on practice problems. So they just give you essentially it's a piece of code. It's like, what do you think this running time is? And then they give you a nice explanation of it as well. But again, another big one, these ones are very useful too. And in particular, above this section as well, we have a section from the class resizing. And one more thing that I want to focus on, I made it in my note up here. there's a section on strings. And strings are a bit particular in Java because, well, I guess does anyone remember why strings are a bit particular in Java? What are strings in Java? They're that was a while ago, but essentially a string in Java is an array of characters. And what that means is that if you're copying over a string in Java using a regular for loop, you're actually doing it very ineffectively. So in this section, in the building string section, called resizing 2, there's a video called resizing 2. Please make sure that you watch that as well, just to remember the different things about the string buffer that the video covers, and also a bit about why strings are operating as arrays in Java. Essentially, though, you're going to be asked a bit about these types of for loops and timings, and then also about the the various ways to, or excuse me, and then also using strings, building up strings to running times. It's the same type of concept in each of them, though. It's not a huge difference between them because strings at the end of the day are arrays of characters, and you already know how to apply timing analysis to for loops as well. Now you'll notice too that we have the 120 and then the 250. If you saw down there when I changed it from j is less than I to j is less than n and so forth too, you saw the differences. Essentially what we're trying to look for here is the different ways of amortizing this analysis, right? So again, once I get up to these values of let's see if I can break my PC. Good. Yep. So that's where it gets a bit where we can break it a bit. Let me see if I can do this much. Okay, so we were hitting a very large number there, which is unfortunate. But essentially here, you can see that I just amortized analysis focuses on not the specifics of it, right? Like you don't really care about the actual numbers that we're dealing with. You're looking at it in general in time, and amortize how long is it? And again, what are some of the things that we said that we can do to manipulate these items? Well, if I go ahead and introduce this as a geometric series, you'll notice now that let's go ahead. Oh, still running now. You'll notice that you get a different output for it as well. I'm wondering why. Okay, this guy's breaking. Let me pull in another example of this one here for us. Let me do my log n. Cool. Let me do n is equal to 8. And I just wanted to show off logarithmic series. So I'm going ahead and I'm using a geometric series here. I is equal to I times 2. And that means that I'm skipping quite a bit of work, right? And again, the general idea here is that if I'm doing a linear amount of work, if I'm doing an arithmetic series, I'm increasing it by an additional value. I have to go ahead and do my 0, 0, 1, 0, 1, 2, 0, 1, 2, 3, 0, 1, 2, 3, 4. And we called this one this type of right triangle. So that was my arithmetic series. When I do something with multiplication or division, when I'm having the amount of work I have to do, what am I getting? I'm getting this more flat pack series where I go ahead and I list it out. Again, the video that I linked does this during the explanation, but essentially we get something that more so looks like this. And again, you're not getting tests on this, but I just want to show everyone that essentially you're flat packing and you're condensing the amount of numbers that you need to look at and go through. And again, when you insert low numbers like 18, 19, and so forth, it doesn't really do its justice on why it's running that way. Let me see. Did this guy run for us? Cool. So we could see here from the examples I linked to, we see when I have my n is equal to 8, and I use my geometric series here of I times 2, I run it around 3 times. So if I have an input size of 8 and I'm getting a runtime of 3, does anyone know what that is? We spoke about it a bit ago, like near the start of class. Does anyone remember those equations we went through? It's the logarithm, right? So whenever I'm using these i's here, I'm going to actually be getting the logarithm of it. So what is the logarithm of 2 to the 8? It's 3, right? What if I go ahead, increase this up to 16? 1, 2, 3, 4. So now I'm getting the logarithm of 16 after I doubled my size, which is then 4. Now, essentially, if you're encountering scenarios where you have a for loop that is linear at the top, let's just say I is less than n very briefly, and it iterates through it. Let's just say this one is linear. This, for any value of n, it's going to run n times. And let's just say your second nested for loop is actually doing something where it has n divided by 2, where if I'm using either division or logarithming it, I'm going to get the log of n. So now you have this scenario where you're like, okay, well, how I have my n and my log of n. What is that? Well, that's actually n by log of n. And does anyone remember what that type of terminology was in our graph that we dealt with? That was the linear arithmetic one, right? Remember, we had that big graph. You don't need to remember. I have it in our cheat sheet here to look at. Let's see here. It's not a real cheat sheet. It's just a little graph. So I'm not telling anyone I'm giving away cheat sheets. But essentially here we could see that this is where we're falling into, and our kind of log n log n is kind of, it's not the best, but that's kind of where heap sort gets into. And this is where we're kind of staying with some of our more advanced ones. We can see here that linear is a straight line is going to increase, and log of n is almost there with constant time. So again, log of n we're able to achieve with geometric series. Combining geometric and arithmetic series gives us a more linear arithmetic one. Combining two linear series brings us up to horrible. And of course, if you have a triply nested loop, and then if you start using exponents and factorials, you'll get up to here. Don't worry about those ones up here, but O of n is squared, O of n to the third, and O of n to the fourth, and so forth. Those are all quadratic and plus running times. So again, for your final, kind of focus on the different running times of these loops. We already looked at an n log n1. We already saw an n1, and we already saw a log of n1. How do I go about and see my O of 1 if constant? Well, again, that is where we just have this type of constant operation, which is essentially an operation of the following, where if I have my int val is equal to 4, and then standard out dot print line val, this is actually a constant time operation, because how much time does it take to run it? Well, it's instant. The access to it is instant, so it's constant. And again, try to look at a few of these on the examples online too. Look at more of these double nested ones, but definitely inside of Union Find, take a look at those. And also with these running times one in the resizing arrays portion. So what I would say in the video up here, when you watch this video in class of resizing, open up the Java files and kind of play around with them a little bit and see what you can get there as well. Great. One more thing, everyone. Before, it's more so for practice. Let me see here. I went ahead and I pushed back the my deck sort, because I know we're busy with other finals and everything, to the Sunday, November 21st, right? Yeah, Sunday's November 21st. There's also a small homework assignment called heap problems that you can just do on scratch paper or paper yourself. And it's just a few of these ones here. Let me see here. If you don't get them all correct, it's fine, but make sure that you focus on the star ones. So there's a few with an asterisk or a star by them: 2.4.9, 2.4.15, and 0.27. And essentially what those are is kind of introducing a few more of the heap sort stuff, doing what we did today. And I really just want people to be exposed more to these heaps ideas so that you're a bit more prepped for 301 as well, because heaps are kind of earlier on in that. So definitely get a good grip of trees, what they're doing, how they're implemented with these arrays and so forth too. These ones are due November 21st as well. These are good practice for your final as well, just to get a general idea, and making sure just submit them as a PDF or anything into the folder there. Make sure you focus on the My Deck Sort one a bit earlier though. But again, just wanted everyone to be aware of this checklist too. Excellent, everyone. So I'll go ahead and let me stop sharing there.